Okay, so today's lecture we will continue on the complex power analysis. So basically, as we know, the complex power S bar equals V bar times I bar conjugate, and it can be converted to real part P plus JQ, rectangular coordinates, or polar coordinates, which is S angle theta, such that S is the apparent power, and its unit in volt ampere. Theta is the power factor angle in degrees. P is the real power in watts. Q is the reactive power in var. Then the overall S bar is called complex power, and the complex power in volt ampere, the units. Now, we know the power, complex power, can be either absorbed or supplied power. So it depends on the element. If you see the element, it is the current leaving the positive, then the positive part of the voltage polarity, then this is S supplied power. While if the current's leaving the here it's entering the leaving the positive. Yeah, if it is entering the positive, then S is absorbing power. So we know this from the power analysis. By here, just we apply for the complex power. The second thing that we can find here, we can apply it for the voltage source and the current source. Now, the next thing is to find the complex power for the passive elements like inductor, capacitor, resistor. What should I do? How can I calculate the complex power for inductor, capacitor, and resistor? We know R, L, or C. In phasor domain, there will be Z, right? Such that for the resistor, Z will be R, inductor, J omega L, capacitor 1 over J omega C, right? So we don't need to worry about is it inductor or resistor or capacitor. Okay, what should I do? The best case is to say we will find for Z bar, and that's it. What's Z bar? You can substitute the corresponding value based on your conversion. Then, what should I do? We know in Ohm's law, V bar equals to I bar times Z bar. And we know S bar equals to V bar times I bar conjugate. Now let's substitute Z bar or Ohm's law into the complex power formula. This yields complex power can be as I squared as a magnitude without the angle times Z bar, or it can be V squared as a magnitude without the angle over Z bar conjugates, or it can be again V bar times I bar conjugates. Okay? That's the formula that we need to use, and it's valid for inductor, resistor, capacitor. Okay? Now, we have something that we need to worry about. Keep in mind, like in V squared over Z bar, we will do the conjugate for Z. And the second thing, which is here, we do the absolute value. Here, absolute value. So keep in mind the absolute value is important. What do I mean by the absolute value? Means only put the magnitude. Don't put the angle. If you have the number written in polar, put only the magnitude. If you have the number is written in rectangular coordinates, convert it to polar and take only the magnitude. So this will be I squared as a magnitude without the angle times Z bar. Then for the other one, V squared as a magnitude over Z bar conjugates. So where should I put the complex number? Wherever you see bar, then put the complex number. While here I squared, do you see bar on I? No. Therefore, don't put the angle. Okay? Then I can apply this using this formula to any other passive element. So we will say, even like here, I don't need to use these notes. I can write it here. Whenever we have resistor, then Z of the resistor will equal to R. Therefore, S bar will be I squared as a magnitude times R, or V squared as a magnitude over R conjugate, and R conjugate is the same as R because it's only real number. Then whenever we have inductor, so Z inductor will be J omega L. Then S bar will be I squared as a magnitude times J omega L, or it can be V squared over j omega L conjugate means puts negative j omega L. And we know 1 over j equal to negative j. So 1 over negative j will be j. So it will be j v squared over omega L. That's for the inductor. Now for the capacitor, the capacitor equals to 1 over j omega c. Then what should I do? When I say S bar, it will be I squared divided or times 1 over j omega c. Or when we calculate V, or to calculate the voltages, I'm sorry, using the voltage formula, V squared over 1 over j omega c. Then it will be j omega c times V squared. Okay? Yes?
Is that not negative JWL? It's positive.
Where? Which one? In the
Top of the
inductor here. Here, negative j omega L. Then 1 over j equal to negative j. So whenever we move 1 over j to the other side, it will be negative j. And there is a negative sign. Negative and negative will cancel each other. We'll make it positive. So I will say 1 over negative j equal to positive j. Then, those are the formulas for resistors, inductors, capacitors. You don't need to memorize anything. You see what I boxed in the green? That's what you need to do. That's what you need to memorize. Then the rest, you will derive it using, we know what's ZL, we know what's ZR, we know what's ZC, and that's it. So that's in summary. So I would say like, whenever we have resistor, inductor, capacitor, like I prefer to use the formula again, S equal I squared times V bar. That's my favorite formula. If you want to use other formula, that's fine. So for example, for the resistor, it was I squared times R. For the inductor, it was I squared times j omega L. For the capacitor, it was I squared divided by j omega c. Then let's try to make a comparison. So we know this is S bar. Let's try to see, because we know S bar is P plus JQ. What will happen to the resistor? The resistor, I squared times R plus J0, because there is no imaginary parts. For the inductor, I squared times j omega L, or I can put j on the other side, j omega L. Then what's else? Is there any real parts? No real parts, so it will be plus 0. While for the capacitor, I can write it as negative j I squared over omega c. So it will be as 0 minus j I squared over omega c. What's the point of writing this, to this as this formula? Because I would like to compare P plus JQ. Here is Q, or JQ plus P. P plus JQ, something like that. So the conclusion for the resistor, P equal I squared times R. Q equal to 0. What does P mean? Real power, I squared times R. What's Q? What does Q mean? Q equal to 0, reactive power. Then for the other thing, for the inductor, P equal to 0, Q equal to I squared times omega L. The capacitor, P equal to 0, Q equal negative I squared over omega C. Okay. So we can conclude something. P, real power for the inductor and the capacitors are zeros. Reactive power for the resistors is 0 as well. Then we can use this conclusion. If you see any question in the homework problem or whatever you see, then find the real power for the inductor. Find the real power for the capacitor. So the answer, you don't need to find anything. You say the real power for the inductor is not consuming any real power. Then it will be 0. Actually, that will be consistent in what we used to see in DC circuits. How? In DC circuits, frequency equal to 0 or omega equal to 0. So what does this mean? We will see that for the resistor, P equal I squared times R. For the inductor, P equal to 0. Capacitor, P equal to 0. And that's consistent with what we used to see in DC. In DC, we used to say whenever we see inductor, replace it by short circuit. Whenever we see capacitor, replace it by open circuit. And the power for each element will be 0. And that's consistent with what we see here. As a result, the inductor and capacitor are not consuming real power. You remember like the last lecture when I mentioned about the chips, Lay's chips, the real power is the actual chips that you eat. The reactive power is the gas inside the chips to keep it fresh. So the inductors and the capacitors, they are actually not consuming real power. They are consuming reactive power, while the resistors are consuming the real power. Okay? And the resistors and resistors, they cannot consume reactive power. That's for the ideal model. For the practical model, it will be something different. I'm talking about the ideal, that's what it will be. Okay? Okay, so to summarize my analysis, what should I do to calculate the complex power? We can follow the following steps. So I can rewrite the I can write the steps here. Step number 1, to calculate the power, convert the circuits to phasor domain. Any voltage source, current source, phasor domain, any resistor, inductor, capacitor will be impedance. The second thing, find all currents, maybe voltages if you need, in the circuits. If you need to calculate all of the elements. If you need for a certain element, then just for the certain element, whatever, depending on what you need. Then, number 3, for sources, you will use S equal V times I conjugates. And depending on is it supplying or absorbing. While for the passive elements, resistors, inductors, capacitors, you will use I squared times Z bar or V squared as a magnitude over Z bar conjugates. Or if you want, you can use V times I. V times I conjugates. Whatever you want to use, or whatever you feel more convenient. So if you know the currents, you can say I squared as a magnitude times Z bar. There is no need to calculate the voltage. Stop here. If you know both voltages and currents, you can say V times I conjugate. If you know only the voltage, you can say V squared over Z bar conjugate. So again, this is similar to what we discussed in DC, but it's just like use whatever you need. Okay? Does this make sense? How about if the question says find the real power? If the question didn't ask you to find the reactive power, just find the real power. The first thing, whenever you see any inductor or capacitor, you will say the real power will be 0. So here, if question say find P, then at the beginning of the question, you will say for L and C, P equal to 0. For the resistor, how can I find the real power? I encourage you to find the complex power first. Then you will say complex power equal P plus JQ. Then take the real parts. Okay? How about if the question says find the reactive power? So whenever you have a resistor, you will say direct the reactive power equal to 0. How about for inductor capacitor? I encourage you to do which is calculate the complex power and convert this to rectangular coordinate, P plus JQ. Then take the imaginary part. This is the reactive power. So the overall, whatever you see any question, find apparent power, find power factor, find anything. Find S bar first. And we know how to do the conversion. We know how to convert this to polar. We know how to convert this to rectangular coordinates. Is this correct? Then if you see any question also like find S without bar, so you will find S first, then you will say S will be S angle theta. And the same thing if you need to calculate theta, that's theta. Okay, does this make sense? So whatever you see any question, find real power, reactive power, apparent power, power factor angle, complex power, the first step, find S bar first. Then, after that, you can convert this to polar, rectangular, and do the conversion. So you can even like write this in your note card, write the formula like how to convert this to polar to rectangular, or you can write whatever you need. Then that's it. So you are not required even to memorize this. Any questions? Okay, so you remember Tillich's theorem? Tillich's theorem, the sum of the power absorbed equal to 0 for all of the circuits. So the sum of the complex power absorbed equal to 0, and which is converted to rectangular, the sum of P plus JQ equal to 0. As a result, this means the sum of P equal to 0, the sum of Q equal to 0. Okay. What you need to apply, just keep in mind the sum of the absorbing power will be 0, and that's it. Now, I'm ready to do to go for examples. But before going to examples, I would like just to mention about some important notations that we need to do in order to solve the AC circuits. Whenever we do solve for voltages, currents, every time your final answer must be in polar form. Whenever we are dealing with impedance and complex power, rectangular form. Okay? This is a must. When you box your final answer for the complex power or the impedance, this will be in rectangular coordinates, while for the voltages and the currents, this must be in polar form. While during your analysis, if you are not boxing that, so during your analysis, you are free to use what form you need. Okay, but what I encourage you is to be consistent. Voltages and currents every time, even during your analysis, I encourage you to keep it in polar. But in case, if you don't want, that's fine. Just I'm talking about when you box your final answer. Let's see an example. Determine the complex power supplied by each element in this circuit and verify Tillich's theorem. So actually, this circuit, we already solved it in chapter 7. So basically, we assume this is as IS1, we assume this as I1 bar, we assume this as I2 bar. In chapter 7, on chapter 5 actually, we calculated IS1 bar. You can go back to the recording and see how we did this calculation. So it was 8.77, angle negative 15.26 degrees ampere. And I1, we calculated it as 6.2, angle negative 60.26 degrees. Then if we need to calculate I2 according to KCL, will be IS minus I1 bar. So as a result, IS will be 6.2, angle 30 degrees amperes. Okay? That's the currents. Now, our target is to calculate the complex power. You have another option, is to calculate all of the voltages. Then you can say S will be V times I conjugates. That's one option. But this is, I consider this is the long method, which is, I think, this is unnecessary. Why do I need to do this? Okay. What should I do? You can just use I squared times Z. That's it. Again, how we did calculate IS, basically, we converted this to Z equivalents, and we calculated IS using Ohm's law. Just for information. Now, I'm ready to do which is the calculate the power for each element. So I can call this as element source. This is, I can call it as element 1, element 2, element 3, element 4. And I need to calculate the complex power for all of these elements. So starting from element S. Now look at the source. The current leaving the positive, this means it is supplying, right? Whenever, recall the supplying power definition, when the current leaving the positive, then this is supplying. So I would say here, to calculate the power of the source, S source supplying will be V source times I source conjugates. In the source, I cannot say I squared times Z because there is no Z for the source, unless if you say use Z equivalent, but I prefer to use V source times I source conjugate, and it is positive because it's supplying. Then it will be 100 angle 0 times 8.77 angle negative 15.26 conjugates. The common mistake in the exam, second exam, which is many students missing the conjugates. So what should I do to deal with this expression in the calculator? So the first thing, before supplying or applying this in the calculator, do the conjugate first. So which will be 100 angle 0 times 8.77 angle. The conjugate means flip the sign of the angle. So it's going to be positive 15.26. Now I'm ready to apply this in the calculator. Even with this one, I can do it easy without the need to put the whole complex numbers. Basically, I can multiply the real parts or the magnitudes together and sum the angles together. So 8.77 times 100 will be 877. Angle 0 plus 1526 degrees, amperes. Then here, I saved a lot of time other than entering this in the calculator and spending too much time on it. So sometimes you need to be try to be your best to make it as easy as possible. Now, remember, the power must be written in rectangular coordinates. This one is in polar. Now you need to use your calculator. Let's convert this to polar, and again, the unit here is volt ampere. So it will be as 846.1 plus J 230.8 volts amperes. Okay? This is the first one. Now the second one for element 1, the other elements are absorbing power, not supplying. Because we know the resistors are absorbing power, then the same thing for the passive elements. So let's start with the element 1, which is the 8 ohm resistor, and I'm talking about the absorbing, not the supplying. So it will be as I square. Let's see the current flowing in I1. This is 1, 2, 3, 4. So the current here is IS flowing with I1. So it will be IS as a magnitude square times Z1 bar. So IS, only substitute the magnitude. Don't say 8.77 angle negative 15.26 square times Z1, which is here, which is 8. Don't say this. Why? Because only we will use the magnitude. Use magnitude, the magnitude. What do I mean by the magnitude? It will be 8.77 without the angle square times Z1 bar, which is 8. That's it. So the answer here, let me try, I'm calculating the supplying. So if I need to say the power supplying, we need to put the negative sign. Why I put the negative sign? Because the resistors or the passive elements, every time, whenever you calculate the power, will be put a negative sign. Okay, for the supply, for the supplying. Absorbing will be positive. Then the answer will be negative 615 volt ampere. That's it. And this is only real part. If you need to talk about the imaginary part, it will be plus J0. Because there is no J element, so plus J0. Again, just recall S bar equals to I square times Z bar or V square over Z bar conjugate. This is for the absorbing. While the supplying, put a negative sign. Negative I square times Z bar or negative V square over Z bar conjugates. So for the supplying, we will put a negative sign. Okay? Now, how about the other elements? So the other elements, which is element number 2, let's see where is element number 2. Here, which is negative J4, and the current flowing is I1. So it will be I1 square as a magnitude times Z2 bar. So S supplying, S element 2 supplying, it will be I1 square times Z2 bar, and don't forget the negative sign because it is not supplying power. Then it will be negative I1 square. I1 is 6.2. We don't need to put the angle, just put the magnitude 6.2 square times Z2 bar, which is Z2 here negative J4. Negative J4. So the results will be J153.8, and the unit is volts amperes. Now element number 3. Element number 3, go to the circuits. Here is number 3, which is the same current, I1, flowing in element number 3. So supplying will be negative I1 square times Z3 bar. So negative I1 square, I1 is given, we already know, as 6.2 square, times Z3 bar, which is J10. So the answer will be, let's see, Z3, J10, which will be, I think, negative J 384.4 volts amperes. Now then the last one, which is element number 4, the current flowing here is called I2 bar. Then it will be I2 square times Z4. So the supplying power by element number 4, which is negative because this element is absorbing. So negative I2 square times Z4 bar, which is going to be negative I2 is 6.2 as a magnitude, then to put the angle, times Z4 bar. Z4 bar is 6. So the answer will be negative 200 or 230.8 volts amperes. Now let's verify intelligence. This means to verify intelligence, we will say the sum of the power supplying equal to 0, or the same also absorbing. So we can say S source 1 plus S1 supplied plus S2 supplied plus S3 supplied plus S4 supplied, they must be 0. So you can validate your or substitute these numbers, so you will end up having this as a 0. Okay? If not, then check your answers, check your numbers. Okay, any question? Okay, let's go to the next example. The second example is very similar to the last lecture. So in previous lecture, I think it was lecture number 17, whatever it's called. So we did calculate the currents as, this was I source. And we call this as I1 bar. We call this as I2 bar. This one as I3 bar. This one as I4 bar. So I source was 4.12, angle negative 30.96 degrees amperes. I1 bar, don't forget the bars, will be 2.91, angle negative 75.96 degrees amperes. We already calculated this before. I2 bar 2.91, angle 14.04 degrees amperes. I3 bar equals to 8.23, angle negative 30.96 degrees amperes. I4 equals to 4.12, angle 149.04 degrees amperes. So the first step, convert this to phasor. The second step, find the currents. Then the third step, I can calculate the power. So how to calculate the complex power? Okay, we can say, let's start with the source. And I can call this as element 1. This is as element 2. This is 3. This is 4. And this is S. So I'm calculating the power absorbed. So for the source, it is supplying, not absorbing. Therefore, S source will be negative V source times I source conjugates, which is going to be negative 12 angle 0 times I source 4.12 angle negative 30.96 degrees conjugates. So I encourage you to do the conjugate first, negative 12 angle 0 times 4.12 angle plus positive 30.96 degrees. Then after substituting this and convert this to rectangular coordinates, it will be negative 42.4 minus J25.4, and then it is volts amperes. How about the other elements? So the other elements, let's start, we have an element here, I'm going to call it A, element A. So S elements A, it is IS squared times ZA, which is 4.12 square times 2. Then it's going to be 33.91 volt ampere. S, this is element A, element 1, element 2, element 3, element 4. Then I can call this as I1. Here is I source. This is I1. Here it is I2. Here is I4. Here is I3. Then to calculate for element 1, all of them are the absorbing power. Then it will be as I1 squared times Z1 bar as a magnitude. So since I didn't put the bar, then it will be only the magnitude. So it will be 2.91 squared times 1. So it will be 8.47 volts amperes. As for element 2 will be I2 squared times Z2 bar. Then it's going to be 2.91 squared, only the magnitude, while Z put the number, which is negative J1. So the answer will be negative J 8.47 volts amperes. As for element 3, it is I3 squared times Z3 bar, which is going to be as 8.23 squared times J1. So it will be J 67.73 volts amperes. Then the last one, which is element 4, I don't have space, I can write it here. S4 bar will be I4 squared times Z4 bar, which will be 4.12 squared, only the magnitude, didn't put the angle, while Z bar put the overall complex number, which is negative J2. So it will be negative J 33.91 volts amperes. Okay? Then that's how we calculate it. Then the last thing, which is do the sum of the power absorbed equal to 0. This means S source plus SA plus S1 plus S2 plus S3 plus S4 must be 0. If not, then definitely there is something wrong. And the last thing, just I encourage you to go to worksheet number 10. You can try it at home. Worksheet number 10. Okay, so you can, it's very important to have a look at it. There is summarizing some procedures, and there's an example written in detail. So you can just use this as a supplementary note, and you can try to solve that example by yourself, then look at the answers. Any questions? Okay, so the next lecture will be the power